don't we get started, just because we're tethered to people who might be signing on online. I think there's 2 talks probably in this session. So Peter Richtarik will start with the first one and tell us about stochastic quasi-gradient methods.
So thank you very much for inviting me. It's always a pleasure to be back at Simon's Institute. I'll speak about something which is mainly about optimization, and it's about optimization motivated by machine learning problems, by training machine learning models. But there'll be a fair amount of randomized numerical algebra behind this particular algorithm. So the title is Stochastic Quasi-Gradient Methods. By quasi-gradient methods, I mean, imagine quasi-Newton methods. Quasi-Newton methods, what they try to do, they try to approximate Newton step in a cheap way. So that you look at the Hessian and you do a certain operation with the Hessian, and you don't want to invert the Hessian exactly, so you do some tricky step and an approximation, and you call this a quasi-Newton approximation. So we do the same thing also with the matrix, but not with the Hessian, but with the Jacobian. So in fact, the step can be seen as a very similar step to what Newton methods do, but with a Jacobian. This algorithm will be variance reduced. So those of you who know what that means, it's another point of view at variance reduction in stochastic optimization. If you haven't seen this, I'll talk about it anyway. Okay, so this is the paper. This is joint work with Robert Gower and Francis Bach. Right, so the outline, first I introduce the problem, the stochastic optimization problem, which is an empirical risk minimization problem. And then the second part, I'll talk about Jacobian sketching. So this is the part where the randomized numerical algebra step comes in. And this is one way of looking at how we develop the algorithm called JacSketch. This controlled stochastic reformulations part is a completely equivalent way to develop and understand the same algorithm, but from a different perspective. And then I'll do a comparison of JacSketch and some special cases of JacSketch, such as SAGA, and show that, in fact, we can improve on some of the best-known bounds for SAGA and resolve some conjectures as well, while giving a generic, overarching approach to variance reduction. Okay, so here's the problem. And the problem is minimize average of a huge number of functions. These are loss functions, and each function has to do with one data point and a label. But I'll abstract from this. For instance, you can have L2 regularized least squares, then the loss function will be like this. So this is the ith label, ith data point, and here everything is linear. So there's a linear predictor. I will assume, in fact, throughout the whole talk, that all of these functions are convex. In fact, you have strong convexity for the entire function f. Now, many of these ideas can be extended. I believe they can be extended to just weakly convex functions and non-convex functions and so on. But there's many new ideas behind this, so I want to analyze the simplest possible case of this problem. Here, another problem would be L2 regularized logistic regressions. These are the kinds of problems we're looking at. All right, so the basic workhorse for empirical risk minimization is gradient descent or variations of gradient descent, where you replace the gradient by something else. And usually you replace this by an unbiased estimator of the gradient in some way or another. And there's many ways of doing that. The simplest way of doing that is simply go back here and sample one I uniformly at random. This is already written as a discrete expectation with uniform probabilities over these I and data points. So in fact, you can just sample I uniformly at random, take gradient of one function fi, and by doing that, you get an unbiased estimator of the gradient. This is not necessarily very good because the variance of this estimator will not diminish throughout the iterative process, so you get a slow algorithm. So the whole point here is to accelerate on that. So if you look at the variance of this estimator, of course it matters. If you use gradient descent, the variance is 0. This is a deterministic algorithm, so everything is good. There's no variance to speak of, but then you have to compute the gradient, and that's the problem, because you have n data points, n could be billions, so you have to take a pass through the entire data set, compute gradient of every single function here, okay, and you want to avoid that. So that's the whole point. Don't do that. Don't take a pass over the data set. SGD, which I already described, sample one I uniformly random, then that will be the unbiased estimate of the gradient, but the variance is big and you don't have really control over it, and it doesn't even diminish to 0 when you're at the optimum. So in fact, when you start the iterative process at the optimum, it will just drive you away. It's an unstable algorithm. The way to kill the variance is to push the step sizes to 0, but then this slows down everything. So the idea is what to do about this. Okay, so graphically, this looks something like this. Okay, GD, SGD goes in these strange directions. These are the stochastic gradients of these individual functions. There's no reason why they should point downwards, but on average they would, and you eventually get there. And the trade-off is these are very, very expensive steps, but they form a nice smooth curve. These are very cheap steps. You have to take many more of them. Okay, now there's several approaches to variance reduction that I know of. The simplest one is just kill the variance through step sizes. Just take step sizes which go down to 0, and in this way, of course, you kill the variance. But of course, the con of this is that this slows down the algorithm, and this is what we want to avoid. Now, another way is mini-batching. Of course, the extreme is that you mini-batch, you compute a full gradient. Okay, this is the full mini-batch. Then you kill the variance completely, but then you pay for it because you have to do the work. You have to compute the gradient of all of those elements in the mini-batch. So that's the problem with that. So we want to avoid that. Another approach would be importance sampling. So maybe don't select one I uniformly at random. Maybe some non-uniform probabilities would actually lead to lower variance. This is yet another approach. So what we'll do here, we'll combine some of these approaches. We'll combine this, and that as well. And we will not work with decreasing step sizes. Adjusting the direction, this is the most significant approach, which started in about 2012. With the SAG method. I don't have it here, SAG, stochastic average gradient. Recently that work won the Lagrange prize in continuous optimization this summer. And all of this work is simply some follow-up, very interesting algorithms motivated by this, achieving the same or very similar results, but through very different approaches. SDCA, stochastic dual coordinate descent, or SVRG, stochastic variance reduced gradient descent, and so on. Okay, so now we're introducing a new approach to variance reduction, and this new approach is motivated through randomized numerical linear algebra. We call it Jacobian sketching, and the algorithm called JacSketch. So this is the idea. So first, we lift the problem, and then we sketch. What do I mean by this? So we generate a function where all of these little functions, f1 through fn, will be put into a vector. So this is a multivariate function. So we lift the problem from 1 dimension to n dimensions. We form the Jacobian of this mapping. Actually, this is the transpose of it, but anyway, I'll just call this the Jacobian. So all the gradients are in the columns. So we lifted everything, and now we look at this Jacobian, and we just think about it for a while. So what is the first observation you might have? The first observation would be, well, if I multiply this by the ith unit basis vector, so everywhere zeros, just one in the ith place, then you get the stochastic gradient that SGD uses. Okay? And the SGD picks I uniformly random. Okay, so that's observation. Another observation is, well, if you multiply this by the vector of all ones divided by n, you get a gradient. Okay? So somehow, of course, this Jacobian contains information which is useful for the estimation of the gradient. And now this has zero variance. This has large, possibly large variance, which doesn't diminish. What else can we do? So the idea of Jacobian sketching is to maintain a sequence of these Jacobians, estimates of these Jacobians, without actually computing them. We'll estimate them. And we will do sketches of the Jacobian, which are cheap. So we'll multiply the true Jacobian from the right by a random matrix. And this information will be used to update our estimate of the Jacobian. Once we have that, we use the Jacobian to estimate a gradient. And then the gradient will be used to take a gradient step. And that's the whole algorithm. Any questions, maybe? Yes?
So the random matrix will be sort of sparse or something like that?
So in general, for the theory, it could be any distribution whatsoever of random matrices, almost any distribution. There's very weak assumptions that we have, and we get a rate for any distribution, but many distributions will just lead to impractical algorithms. So the practical algorithms will be a very small subset of all of this huge class of algorithms. And one possibility is just doing this. Okay, just one vector, and super sparse. Okay, or you can have maybe not one column of the identity matrix, but a random submatrix, column submatrix of the identity matrix. That's another option.
I'm just thinking, you are probably also saving on non-computing whole columns, is that true? Of the gradient, once you pick an I, you compute the entire gradient? Or
No, if I pick an I, then I'm just computing this, and this is the gradient of just a single function.
In your setup, what are you doing? Well, you said you multiply it by a matrix, right?
Right. I'll describe it. So this is something that I'm going to describe. Yeah. Okay. Very good. So that's the idea. So different way of saying this is the following. We want to solve this equation. This is a matrix equation where this is the left-hand side, unknown j, and this is the right-hand side, the true Jacobian. If we knew how to solve this easily, we can just take the j, which is this, multiply it by the vector of all ones, divided by n, and we get a gradient, everything is fine. Okay, we have no issue. So this is one of the simplest possible linear systems in a matrix space, because the operator is just identity here. Okay, you don't have to invert anything. The problem here, even though this is a super simple system, it's difficult to solve because you need to compute every single gradient. You have to actually compute the right-hand side first to solve this. And this is exactly what you want to avoid. You don't want to compute all of these stochastic gradients, n of them, because it's a billion of them. Okay? So we have a super simple linear system which we don't want to solve. Okay? So what do? Well, we do something Kaczmarz-like. So that's the idea. Something like a randomized Kaczmarz step, but just one step. A generalized randomized Kaczmarz step, and this is something which we call sketch and project. So what we do, we multiply the system from the right by a random matrix. Now it can be anything, as I said. And then this is what we measure. So it has to be a random matrix where we're willing to compute this action of the Jacobian on this random matrix. So of course, if you want this to be practical, then this has to be something very special. But for the theory, it could be anything. And then we solve for j. Now this will have an infinity of solutions. This has just a single solution. This will have infinity of solutions. So how do you pick from this infinity of solutions? Well, we build a learning process into this. So what we do, just like randomized Kaczmarz, we take the previous estimate of j and we project it onto the solution space of this. And that's going to be the new estimate. Okay? That's the whole idea. So what we do, we sample this thing and project it back. And this is described here. So this is the previous estimate, jk, which we built throughout the process. And this is the sketched linear system. And this is the projection. So if you look at this same thing, but not in a matrix setup, in standard linear systems setup, and this sk is just the ith unit coordinate vector, this would be the randomized Kaczmarz method. Okay.
What's the norm there?
So this would be Frobenius norm. It would be some weighted Frobenius norm in general, but here I'm choosing non-weighted Frobenius norm. Okay, so that's it. We call this step sketch and project because you sketch the system and you project onto it. And of course, by doing this one step, we have not solved the original system. We have not done it, but we've taken one step of a randomized method towards solving the system. But then we take the optimization step. Now the Jacobian changes, and then we take the randomized numerical linear algebra step, and we'll alternate these. Hopefully, these JKs will converge to the true Jacobian at the optimum, and they will. And hopefully, the optimization problem will be solved at the same time. So we're solving linear algebra and optimization problem at the same time. In fact, the Lyapunov function that will go to 0 is a combination of the two. Okay, so that's it. So this has an explicit solution. Can be written down in this way. This is the previous estimator plus the difference of the previous estimator and the true Jacobian times certain projection matrix, just projection onto the range space of SK. Yes?
You probably said this, but what's the structure on SK? Is it sparse, structured in any way?
Yeah, so for now, for the theory, it can be anything. And this is in fact where many open problems now still are, because we didn't go and exploit this. Could be many sketching matrices could be used here, and maybe better rates could be obtained. So what we've done, we've just written down the generic formulae for any distribution, and then we look at a few special cases, and that's it. And not even very elaborate special cases. So, and if you want this to be practical, then yes, the best example to think of is think of SK as a random column submatrix of the identity matrix with just few columns. This would lead to something which is called the Minibatch SAGA method. And this is a very practical method which has the same performance as any of the state-of-the-art variance reduced methods. Okay. So this is the whole Jacobian learning step. And now we use the Jacobian to estimate the gradient. Okay? So how do we do that? Actually, maybe I should say something about sketch and project. So we've been working on these sketch and project iterations for a while, and on things similar to this. And we've written a bunch of papers, starting with this paper with Robert, Randomized Iterative Methods for Linear Systems. Then we look at the duality behind this. Then we look at application to quasi-Newton methods and matrix inversion. We look at applications to machine learning, and so on and so forth. One of the last things, for instance, that we looked at was coming up with formulae for accelerated quasi-Newton updates for matrix inversion, and so on. So there's lots of interesting things that can be done with these types of iterations. One can generalize linear feasibility to convex feasibility in a tight way, and so on. So I don't want to go there. If anybody's interested, I'm happy to talk about this later on. All right, so now that we have the JK, we have to use it. We want to use it to estimate a gradient, and this is how we're going to do it. So forget about this part. Imagine that theta is just 0, actually 1, okay? Theta is 1. So this is not there. And then what happens is that you just multiply the Jacobian, the latest one that you have, by the vector of all ones divided by n. If this was the true Jacobian, then this would be the true gradient, and everything is perfect, okay? Now, why do we have this convex combination of the previous estimate and the new one? This is because we want the estimator, GK, to be unbiased estimator of the gradient. It turns out we have to do it this way. If you didn't do it this way, if theta was 1, then the algorithm would be equivalent that you get out of this for very special sketching matrices SK to the SAG method, stochastic average gradient, which uses bias estimator of the gradient. This is notoriously difficult to analyze. Okay, so it turns out once you plug this formula for JK plus 1 that I had on one of these previous slides into this, this is what you get. And now, okay, what is what? So you can very easily see that, in fact, this is unbiased estimate of the gradient. How? Well, take an expectation of this. Where's the randomization? It's only in SK. So just in these two things. So now, by linearity, you can go all the way here and compute the expectation of this. And we will assume about this that the expectation of this is the vector of all ones, so E. That's going to be an assumption. Once you have that, you get an E here. This part cancels out with this, and you just get this multiplied by E divided N, which is the exact gradient. So you get an unbiased estimate of the gradient. So we call this condition bias correction. And we call this theta SK bias correcting random variable if it has this property. And there always exists something like that. Of course, it will depend on the distribution and so on. Okay, so that's the idea. And then use this GK to do exactly what I said on the first slide. Just take this gradient step. So that's the whole algorithm. And I'll pause for a moment. Yeah?
Does the data data depends on the choice of S?
Data.
Theta.
So, or theta, yeah, definitely, yeah. So it's a random variable depending on SK. Right. So for instance, if you do this SGD stuff, where you choose one data point uniformly at random, then theta would be 1 over the probability, so it would be n. So in fact, this will not be a convex combination, but it will be a phi combination. Okay? If you choose one I with probably pi, then this theta will be 1 over pi, for instance. Okay. All right. So now this is all I have to say about this connection to randomized numerical linear algebra. Now I'll give a completely different but equivalent development of this algorithm, motivation behind this algorithm, what's going on from a different point of view. And we call this the stochastic reformulation point of view. And the idea is this. We start with this deterministic problem of ERM, of just average of functions, and we inject randomness into it, so we complicate our lives. We start with something very simple, there's not randomness there, and we make it into a stochastic optimization problem. Okay? How do we do it? Well, we first use the lifting step right here, and we take in the product between this and the vector of all ones. Then we use the bias correction step, where we write E as an expectation. So we just write vector of all ones as a mean of some random vectors. Okay, then we use linearity of expectation right here. We get it out. And now suddenly we have these inner functions, which we can call fs. And we say, okay, we have a stochastic optimization problem. Minimize this expectation. This is completely equivalent to minimizing f. But stochastic gradient descent applied to this problem will be something else, and stochastic gradient descent applied to that one. Because now it will depend on our choice of distribution, and we can play with it. Okay? So this is the original problem. This is the new problem. For any distribution, it's equivalent. Okay, so that's the first step. If you applied SGD to this, what special cases do we get, just to get our intuition right? So if this distribution is just identity to probability 1, okay, so it's deterministic, then it turns out the bias correcting random variable should be 1, and you get gradient descent as a special case. So SGD is gradient descent for a special distribution. Now, if you choose single stochastic gradient with probability pi, then you get SGD, but with non-uniform probabilities. If you now use, okay, you cannot see this, but if you use S to be sum of vectors EI for a random collection of i's, then what you get is a non-uniform mini-batch SGD. Okay, so these are all special cases of this SGD for the stochastic reformulation. Okay, so this is the first point. But if we did this, the method will not be variance reduced. So this would still be problematic. So we have to throw in an additional trick. So the additional trick is something we call controlled stochastic reformulation. So we want to inject into the reformulation our knowledge about the estimate of the Jacobian in order to correct for something, to make this reformulation better. Okay? If you will, you can think of this as preconditioning, because we'll change the reformulation at every iteration using the JK so that it will have a better condition number. But we do this at every single iteration of the algorithm. So this would be adaptive stochastic preconditioning that's happening here. So we change the function in this way. We also inject the blue stuff, the J. And if this was not there, this is the original stochastic reformulation. But with this, we're adding a 0 on average to this. So this is a random variable, okay? But the expectation by design is 0. So we're just adding 0 to the function, but in a very structured way. And in particular, this function zs has the same form as fs, exactly the same form, except wherever we had this nonlinearity fx, we put in a linear term with the Jacobian in there. Okay? So it's a very similar structure. Okay, so this is also, you can think of this as a control variate, which evolves throughout the iterative process. And now we'll apply SGD to this new control stochastic reformulation. And this is the JacSketch algorithm, so the same algorithm that you've seen before. So this is the JacSketch algorithm. Okay. So I'll pause again in case there's any questions.
So that stochastic reformulation was exactly what Jian Yang had in the context of LP regression. He didn't look at the variance reduction, but he had exactly that in the context of LP regression. Okay. So we can follow up.
Sure.
Yeah,
Okay.
that may have been
Happy to
optimal.
talk about it. Yeah. Okay. So some insight into why this is variance reduced. So here's the insight. We have this theorem which says that the variance of this estimator, because this is unbiased, is the variance, is equal to this for some very specific matrix B defined in this way. Okay, don't look into the details what B is, but it depends on the S and so on, okay, on the distribution, etc. So now you can see how can you make this whole variance small? Well, either by choosing the distribution D in such a way that B is small, okay, or by trying to learn the J so that it's close to the Jacobian. So there's two ways, okay? And what we do, what mini-batching does, it only touches B. What importance sampling does, it only affects B, okay? But what Jacobian sketching does, it affects J. Okay? But we can combine mini-batching, importance sampling, and Jacobian sketching at the same time, so we can work with B and J at the same time. Okay, so this is the intuition. I'll skip this. You can give more insight into this when you upper bound it and so on, but I'll just, for the sake of the time, I will not go there. And now I'll go into some special cases. So first special case, this is the JacSketch algorithm, first of all, just written on one slide explicitly. This is the whole thing. So Jacobian sketching step. estimator of the gradient step. That's it. So the special case of JacSketch is the SAGA algorithm, published NIPS 2014. And the SAGA algorithm uses this very particular sketch. So just random column submatrix of the identity matrix, super sparse, so everything is easy to do. So then when you write down the JacSketch algorithm, which is equivalent to Minibatch SAGA algorithm, it looks like just this. So all that's going on is that you maintain these matrices, Jacobians, where every time you compute the stochastic gradient belonging to some random set minibatch that you've chosen, you just replace that column by the stochastic gradient. So the Jacobian estimator always contains in the ith column the latest stochastic gradient at data point I that you have ever computed. That's it. Okay? So it's very, very simple. And then the gradient estimator has this very simple form, and you take the gradient descent step. So that's it. So what can we say about the iteration complexity of JacSketch? And then I come back and compare against what is known about this particular algorithm. So we have this one general theorem which covers any sampling, any sketching. And the general theorem says that if the number of iterations at least this constant times log 1 of epsilon, which means you get linear rate or exponential decay of the error, then certainly the Lyapunov function will go to below epsilon. The Lyapunov function, as I said, contains xk. So this is the distance to the minimizer. And also jk minus the true Jacobian at the optimum. So it solves the linear system. It solves for the Jacobian and for the solution at the same time. So we're truly solving both of these problems. In fact, you can see this as a combination of two SGD algorithms, because this sketch and project step can be seen as the application of SGD to a different stochastic reformulation of the linear system in the matrix space. And this is, of course, SGD for the control stochastic reformulation. This is an interplay of two SGDs on two different problems, which are connected. And now these constants, they all have some definitions, but I don't want to go there. This is just way too much to go into the definition of L1, L2. Mu is strong convexity. Okay, that's easy. But this kappa and rho and L1, L2, these are some novel constants which also depend on the randomization. And they have not entirely simple definitions. But to illustrate what this result would mean, I would go into some special cases. So one special case would be gradient descent. Okay, so if you apply this theorem to the special distribution where you do identity with probably 1, you get gradient descent, and this is the rate that you get, which is exactly the rate of gradient descent. Okay, you have a 4 there, okay, but we're not worried about that. So you get the gradient descent almost perfectly. Okay, so what if you apply SAGA with uniform sampling? Then you get this, and this rate n plus essentially condition number, which is also the known rate of SAGA for uniform sampling. Okay, SAGA has 2 here and 2 here, so it's slight variation, but this is roughly the same thing. So here, there's no surprise. We're not improving anything. We're just checking that, okay, we get in these special cases what is already known. Okay, let's try to improve something now. So if you now use Minibatch SAGA, then you get this rate, and I'm not going to break it down into what's going on. Tau is the Minibatch size, but what I want to say is that this improves on the best known rate for Minibatch SAGA in this NIPS 2015 paper by Hoffman and co-authors. So while we have this very generic point of view, which works for any sampling, any sketching, for the special sketching, we can improve best known results. Now, we have also specialized theorem, which we apply to partition sketches. So this is a partition of all these data points, and we select one partition with some non-uniform probability PCJ. Okay, and then we use sketch matrix, which is the random column submatrix of the identity. Then what we get is a specialized theorem, and this theorem gives you tight results for important sampling. For this, we had to develop a new technique with a stochastic Lyapunov function. I'll not go into the details, but there is something random about this Lyapunov function, which is not just because of jk and xk. Okay, there's an additional randomness. And then when you apply this theorem, then you get the best known results, resolving a conjecture of Mark Schmidt and co-authors in this paper AI Stats 2015, where they said that SAGA with important sampling really should have this kind of a rate, but nobody was able to establish, and we get it as a special case. Okay, so finally, here are the complexity results in the paper. I talked about just some of them. I'll not go there, and just illustrate some experiments. So if we look at regression and we apply our method, this is the SAGA with uniform sampling. This is the saga with the best known importance sampling up to now, the paper that I mentioned. And this is the saga with our importance sampling, which is much better than the best known saga with importance sampling. So this is one example. Another example is on libsvm dataset where we apply Minibatch SAGA. This was the best known Minibatch SAGA performance. This is our Minibatch SAGA performance. Okay, so let's forget about what these things mean, but the point is, as the Minibatch size increases, the gap also increases. And finally, if you apply logistic regression and compare to some other methods, such as SVRG, let's say, SVRG is right here, our method is right here, and these are the two variants of our method. One is the one which uses unbiased estimator, which is the SAGA, and the red one uses an unbiased estimator. So this is the stochastic average gradient estimator. For some reason, this almost always outperforms the unbiased one, but nobody knows why. Okay, that's roughly it. Thank you very much.
Why don't we have a quick question while you want to get set up, and maybe a quick question while we get set up.
So, okay. Yeah, go ahead. Oh, so can you comment on the per epoch time? So you show convergence faster with epochs. So yeah, the rates are faster, but are you paying a lot per iteration compared to SGD or gradient descent?
So there we're not comparing through iterations. The x-axis were not iterations. These were passes through data.
Right.
So
No, but the update. So if I take even the passes over data.
So whenever we are comparing against other algorithms, the one iteration is really the same cost. So we're not comparing uncomparable things. Yeah.
You can show the same thing in the time as well.
Yeah, exactly.
Yeah, because per epoch is usually, I can use Newtons and per epoch.
Of course. No, you can. So the tests were set up in such a way that these steps are very comparable. Almost identical. You just compute one or subset of stochastic gradients, and that's the main cost.
So how can you beat stochastic gradient? Because stochastic gradient is just a
Because of the variance,
point.
because of the variance reduction.
No. So variance is in the epochs, right? But what I'm saying is, what is the per epoch cost? Like stochastic gradient in a sense is like a coin flip.
Yes.
And pick a data.
Yes. So this is the cost here is roughly twice of that.
So you're.
But the number of iterations goes down, decreases much more. If you look at the special case, it would be roughly
So
like
you're
that.
saying the sketch and project just takes 2 random sample or something of that?
Yeah, roughly like that. In the special case, in general, it could be very bad, but in the special case, it's super cheap, and we can take it offline. I can tell you why.
Yeah.
Okay, thank you.
All right, thanks a lot. Let's, there's other questions, let's push them off to the break if that's okay. Just